Welcome to Green Chemistry. In this lesson, we will explore the trade-offs between stoichiometric and catalytic strategies for sustainable reaction mechanisms. We will look at the chemistry, the math, the statistics, and the graphics that help us decide. Here is the big picture. A stoichiometric route uses a reagent in one-to-one proportion with the substrate and makes equivalent waste. A catalytic route uses a tiny amount of catalyst, which turns over many times, and is ideally regenerated by a green oxidant like oxygen. Let us compare a concrete reaction: oxidation of a primary alcohol to an aldehyde. In a stoichiometric route, using dichromate, the reagent is consumed and heavy metal waste is produced. In a catalytic route, a small amount of catalyst cycles. Oxygen accepts the electrons, and the only byproduct is water. The catalyst is regenerated. We can measure sustainability using metrics. Atom economy is the mass of the desired product divided by the mass of all reactants. For the stoichiometric example, 44 over 46 plus 294 gives 12.9%. For the catalytic oxygen route, 44 over 62 gives 71%. E factor is waste over product. Stoichiometric gives about 6.7. Catalytic gives about 0.41. Catalyst strength is measured by TON and TOF. In our example, TON equals 100 and TOF equals 50 per hour. Real processes vary run to run. Let us compare the E factor by experiment. The stoichiometric route averages around 6.74, with a standard deviation about 0.11. The catalytic route averages around 0.43, with a standard deviation about 0.02. We show the means and error bars to summarize variability. Sustainability is often a balancing act. On this chart, the horizontal axis is energy per mole and the vertical axis is E factor. The stoichiometric point sits high in waste and high in energy. Catalytic options form a curve. One uses less energy but a bit more waste. Another uses slightly more energy to reduce waste further. The dashed line shows the Pareto frontier, points where you cannot improve waste without paying energy, or vice versa. To choose among options, we can write a simple model. Impact equals alpha times energy plus beta times E factor plus gamma times metal used per kilogram of product. The weights reflect priorities. For example, if regulations penalize waste heavily, beta is larger. This framework makes the trade-offs explicit and comparable. Mechanistically, catalysts travel a cycle, bind substrate, perform the key redox step with oxygen, and release product while the catalyst is regenerated. This loop is what creates turnover.